It's a very interdisciplinary field, and in order to make these things work, we need all of these contributions. You can't understand what quantum computer is doing without some physics, because you need to know the way quantum systems behave. But if you're writing quantum algorithms, that's a computer science type problem, and you probably need to know something about classical algorithms. But if you're building a quantum computer, you have to figure out how to connect up all the wires. So all of these things are important to building quantum computers. Nobody, again, is going to know everything. But by bringing in people with all these different knowledge bases, we can make a vibrant, exciting field.
Returning listeners of our podcast know that I'm a huge fan of science fiction in any form. And to me, it feels like quantum is one of the most overused words in pop culture when a show wants to sound mysteriously scientific or fantastically high-tech. From the quantum realm in the Marvel Cinematic Universe to Star Trek's quantum torpedoes and the time-traveling show Quantum Leap, writers have intentionally misused the word or at the very least mischaracterized its meaning. So as we dive into our topic today of quantum computing, don't think of time travel, massive explosions, or world-ending viruses, but rather how we actually apply principles of quantum mechanics to create a new way to analyze the world around us. To help us understand what quantum computing truly is and isn't, we have with us today Dr. Daniel Gottesman, the Brin Family Endowed Chair in Theoretical Computer Science at the University of Maryland and the co-director of the Joint Center for Quantum Information and Computer Science. Daniel, welcome to the Tech Between Us.
Thanks. Good to be here.
So to start us off, can you tell us a little bit about yourself and your areas of research?
Sure. So I'm Daniel Gottesman. I'm a professor at the University of Maryland. I'm a Brin Family Chair in Theoretical Computer Science, so I'm in the Computer Science department there. My research is on quantum computing. I've done a variety of things in quantum computing, but one specialty is quantum error correction and fault tolerance.
Quantum is kind of a catch-all phrase for anything high-tech, but quantum computing really, truly relies on the principles of quantum mechanics. So for those of us who may not be as well-versed in the theories of quantum mechanics, what sorts of things do we need to know from that area in order to help us understand what quantum computing is?
Yeah, well, so the laws of physics, when you go down to the level of single atoms, are really quite different from what we're used to in everyday life. So atoms and other microscopic particles like that can be in what's called a superposition, a quantum superposition.
Okay.
And what that means is it's in some sense like being in two states at once, two places at once, or two energy values at once. But another way, it's like choosing between one or the other. So it's not something that has a real classical analog. And so classical analogies kind of break down. And when you have a superposition like this, some interesting things can happen. Like you can have one alternative go one way and the other alternative go the other way, or they can kind of recombine and then they can interfere either constructively or destructively. Like water waves, if you have drop two pebbles in a lake, then you'll get ripples. And when they start to intersect each other, they make interesting patterns. And that's an example of interference. But with quantum mechanics, that can happen with probabilities. Like probabilities can add together or they can subtract from each other. So that's something that can't happen with regular probabilities.
Okay, interesting. So superposition, interference, what other things out of quantum mechanics world would we need to know to better understand the concept of quantum computing?
So another kind of very fundamental quantum concept is that of entanglement. So when you have multiple quantum particles, of course, they can interact with each other and they can develop some correlations. But they can also develop some kinds of correlations that are different from anything that you could get with regular classical objects.
Okay.
And so entanglement is kind of the catch-all notion for the way that two quantum particles can interact with each other, can be correlated with each other. But it can have a stronger correlation than anything you could get classically. And so, if you read popular science books about quantum mechanics, there might be a lot of confusing stuff about faster than light travel and stuff like that. That's not exactly right. Like you can't, if you have two entangled quantum particles, if you do something here, you can't tell for this other particle if anything happened to it or not. But if you make measurements on both particles, you can see a correlation.
Okay.
And in certain cases, that correlation can be stronger than anything you could possibly have if they were just classical particles.
Okay. So if you measure, for example, one particle as, say up, so if they're entangled, would that guarantee that the second one would be, up or down or whatever that is?
Yeah, so there's lots of different kinds of entangled states. So you can certainly have entangled states where one particle is up and the other particle, then if you measure it to be up, then you know that the other particle must also be up.
Got it. Okay.
But that itself is just like classical correlation, right? Like you could have two people with their thumbs and you say, okay, we're going to agree that we're going to both put them up or both put them down. And then, maybe you don't know whether they're going to put them up or down, but once you see one of them, you know what the other one is. But quantum particles can have more complicated correlations where there's like different things you could measure about a quantum state. But another important aspect of quantum mechanics is that when you measure a quantum state, it disturbs it. So you can't measure everything about a quantum state because one measurement kind of excludes other measurements that you might want to make. It changes the state before you have a chance to make those other measurements. And despite this wide range of measurements, if you measure one thing on one particle and you measure a different thing on the other particle, that's when you can see some really unusual quantum effects.
Interesting. So are quantum computers set up, physically and structurally similar to classical computers? In other words, do you have quantum memory and CPUs and things like that? Or are they just a completely different creature altogether?
They'll have some of the same structure as a regular classical computer. But one thing that quantum computers are still in development, right? There's a lot of companies, both big tech companies and smaller startup companies that are trying to build quantum computers. And there's lots of different ways that people are trying. There's at least 4 or 5 completely different kinds of systems that people are using to try to build quantum computers. There's superconductors and ion traps and cold atoms and photons and some others. We don't know which of these is going to be the winner, like in terms of which technology.
Is there any way to combine the different architectures into a single, one that where the weaknesses of one offset the strengths of another, vice versa?
That's another possibility. So first of all, there could be different kinds of quantum computers for different applications. Like ones that need to interface with communications devices. Maybe photons are going to be good for that. But also, we are going to need to kind of put together different modules of quantum computing into a bigger system because there's kind of a limit to how big you can make each kind of processor unit. Which is different for the different types. But then we have to connect them up, and that process also, involves changing your quantum information from one type to another. And so we might well develop good interfaces between these different types of quantum computers and be able to combine them into a single device.
What sorts of things do you see quantum computers being good at and being used specifically for alongside classical computing?
Right. So one thing that's very important about quantum computers is it's not just a faster computer. Like we're used to, of course, new generations of computers coming out and it's faster, and then it's faster at everything. Maybe there's some things it has a little bit specialized circuitry for, and some things that it's not. But quantum computers are not like that. There's some things that they're really, really, really good at.
Okay.
And so there's examples of that are breaking a lot of cryptographic schemes. RSA is kind of one of the more widely used encryption schemes in the world today, but it's insecure if the person that's trying to break it has a quantum computer. And so that's one thing. We hope that people won't be running that because we hope that people will change cryptographic schemes to use ones that are more secure, that would work even against quantum computers.
Are there new schemes coming out, or are there new schemes being developed that are, I guess, better against quantum computers? Yes.
So NIST has now created a new standard for what's called post-quantum cryptography. And post-quantum cryptography is just regular cryptography, but it's cryptography that we think will be secure against quantum computers. And so the recommendation is that everybody should change to using these post-quantum cryptographic schemes. And I think NIST is recommending by 2030 or something like that to definitely be doing it. There's been some recent progress in quantum computers, so probably sooner is better than later.
Dive deeper into quantum computing with Mauser's ebook on the subject, Engineering the Quantum Future. It examines the fundamentals, what it is, why it's important, and how it aims to revolutionize industries from pharmaceuticals to finance to cybersecurity and beyond. Leap into the quantum future and read it by visiting resources.mauser.com/methods. What would be an example of something that a scientist or a materials researcher would use a quantum computer to try to do?
For instance, if you're interested in trying to develop a new material that has some, interesting properties,
Okay.
what you might do is you might say, okay, let me try some structures of what if the atoms are connected this way? How will that system behave? And that's the problem that can be very hard to solve on a classical computer because, understanding the behavior of atoms requires us to understand this quantum mechanics stuff. And while we can write down the equations for that, actually solving them to simulate what would actually happen is beyond the classical computer, because that's something that the quantum computer is really good at, and the classical computer is not.
So there's a list of we think this should be a good problem for a quantum computer to solve, but we're not quite there yet to know for sure.
That's right. If you talk to different people, they will think different things about whether this particular problem will work or not. Yeah.
What's holding us back from getting from, 1 qubit to however many that we need to solve some of these problems?
There's a number of problems. So the first problem just is that, we want to build quantum computers out of microscopic things, right, that behave quantum mechanically.
Uh-huh.
And manipulating single atoms or small numbers of atoms and manufacturing many, devices on that scale, that's technologically a hard thing to do. We're getting better at it. We've gotten a lot better at it. Mm-hmm. So we can do it. But doing it on a big enough scale to make a big quantum computer, that's still a challenge. And the other problem is that another way that quantum mechanics is fundamentally different from classical mechanics is that it's inherently much more sensitive to errors. So obviously, again, dealing with very small things, they're going to be more vulnerable to errors anyway, because if there's just one atom, it just takes this really small nudge to change it from an up to a down, which would change your qubit in the quantum computer. And that can be enough to ruin your whole quantum computation.
Wow, just a single stray atom just happens to kind of float into wherever you are. It can throw an entire computation off?
Yeah, if you're not careful. And so the solution to this is something called quantum error correction. This is something that I work on. And the idea there is that we can encode our quantum computers by having extra qubits and put them in some special entangled state that's more resistant to these errors, so that we're able to identify when errors happen, whether they're errors caused by kind of regular classical processes of just flipping a bit, or whether they're one of these decoherence errors that's involving a measurement that was not supposed to happen. And then once we can identify the errors, then we can correct them. But then, of course, we also need to be able to do computations while we're protected against these errors. That's something called fault tolerance. And we think that it will not be possible to build a big quantum computer without these fault-tolerant techniques. And we're kind of at that stage today. And so people are starting to implement these fault-tolerant protocols in real devices. And of course, then there's a lot of other challenges, both in building a quantum computer and running it. I mean, you have to keep this quantum computer running for those months because you can't store the quantum information on regular classical hard drives. And so if you have a power outage and it goes and everything stops, then you have to start over.
Wow. So there is no such thing as non-volatile memory for quantum computers.
That's right.
Oh, interesting. Well, I was not aware of that at all. Daniel, where do you see quantum computing going in 10 years, 20 years from now? I mean, do you see data centers full of quantum computers, or do you think it's still going to be a little bit more of a lab or a research thing?
Well, in the 10-year time scale, I think we'll start to see some of these actual practical applications of quantum computers. Again, they're not going to be stuff that's going to directly be used by most people, that it's going to be this specialized scientific thing. On the 20-year time scale, it's very hard to predict. Once people start to actually build and use lots of quantum computers, it will probably become less expensive to build them. We'll get better at doing that. We'll have bigger ones. We'll have a wider range of applications. And we'll start to see answers to some of these questions of these other problems that quantum computers are good at that right now we can't be sure of.
So you've got quantum computing, you've got artificial intelligence, two probably of the largest areas of interest in computer sciences and computation. Do you see them working well together, or do you see them almost competing for resources and, I guess, mind share?
I don't see quantum computing and AI as competing. I think some AI people do. Mm-hmm. I think some AI people think, well, AI will solve every problem. Right. Those of us in quantum computing don't believe that's true. There's some problems and there's good theoretical reason to believe that there's some computational problems which just cannot be solved on a classical computer. No matter how good AI gets, quantum computers will still have applications. Now, it's quite possible, but again, we don't know, that quantum computers can help train AI, or AI running on a quantum computer can maybe also solve some problems faster than classical AIs could. And so people, of course, are researching that and trying to figure out if that can help. But there's good reasons to believe that they can help each other in that sense.
Okay. So there is a lot of synergies between the two.
Yeah.
Okay.
Yeah.
Danielle, I want to thank you so much for joining us on The Tech Between Us and giving us the insight into quantum computing.
You're welcome. It's been a pleasure.
Thanks for joining us on today's episode. We invite you to subscribe and follow for more content, including articles, blogs, and more by visiting mauser.com/empowering-innovation. Join us on the next episode, where we dive into a topic that's been at the core of modern computing for more than 50 years, Moore's Law. Are we approaching its end, or just entering a new chapter of computing innovation? Stay tuned to find out.